Several weeks ago, we covered the fundamentals of functions, a key idea in math. I recommend before continuing in this video and the next that you watch that video again. Beginning this week, we will start looking at advanced types of functions and their applications to SAT problems. We will start with an example. Marielle throws a baseball and finds that the height of the ball x seconds after being thrown can be given in meters by the function below. What is the greatest height the ball reaches? We're going to solve this problem in a pretty roundabout way by first learning vertex form. Vertex form is another way to represent a quadratic function using what is known as the vertex, which is the maximum or minimum point on a quadratic. For the simplest quadratic function, f of x equals x squared, the vertex is just the origin, 0, 0, and it is a minimum point. Now in this other example, we see the vertex as a maximum point, centered at 5, 4. And we also see in the top corner the written function form, written in vertex form of this quadratic, which we will soon pick apart what each of these numbers means. Another example here, we have a vertex which is a minimum at -3, -3, one more at -5, 2, another minimum. And then the last example here where we generalize to general vertex form of any quadratic function. So when we have a vertex centered at h, k as we see here, we can see the vertex form written for h, k as we have it written right here. So how do we move from standard form of a quadratic function into the vertex form of a quadratic function? Basically, how do we find these parameters a, h, and k? Well, let's start with h, and there's a pretty straightforward way. We can just evaluate it as -b over 2a. This might look like it comes from nowhere, but actually you can remember it as the first half of the quadratic formula as we see here. Next up, we have k, the y value of the vertex. We can simply find that if we know the x value by just plugging it into our function, finding f of h. Straightforward as that. And then lastly, a is actually the same a, which we can just carry over directly from the standard form. Now, let's go ahead and apply this to the problem we saw a minute ago, finding the maximum height of this thrown ball modeled by this function. So we're going to convert this standard form function into its vertex form and use that to determine the maximum height. So we start, again, with h, the x value of the vertex, plugging in -b over 2a from the coefficients of our standard form function, and we get h is equal to 1. Next, we want to find k by evaluating f of h, which is f of 1. We plug that in, we evaluate, and we get 12, as we see here. Now we can plug those numbers into our vertex form, just throwing in the last number a as -10, carrying it over directly. And we get our final vertex form as f of x equals -10 times x minus 1 squared plus 12. There we have our vertex form. So what is our final answer? Well, we're looking for the maximum height that the ball reaches. And the maximum height, note that's the vertex. So we look at the y value of the vertex, which we found is 12. That is our greatest height, and that is our final answer, 12. Now on to another example where we look at polynomials, not just a simple quadratic. This example we see here is a common problem type where we're asked to match a function with its graph. When we're solving problems like these, we want to identify key features of the function and compare it with the features we see on the graphs. Because they're easy to identify on graphs, x and y intercepts are great key features to look for to compare between functions and graphs. As a quick refresher, remember that the y-intercept is where the graph crosses the y-axis, so that's actually when x equals 0. X-intercept crosses the x-axis, and that's when y equals 0. So let's start with our x-intercepts in this example, which was going to be when we set f of x equal to 0. Doing that to our function here, we have a polynomial equation that we should recognize how to solve. Just use zero product property and we get solutions, or x-intercepts, of x equals 0, 2, and -1. So now we can compare these with our graphs. In A, we only have x-intercepts 1 and 2, so that's wrong. In B, the x-intercepts are 0, +1, and +2, which is also wrong. In C, it's -1 and 2, again not matching what we just found from our function. And then lastly, looking at D, we have the correct intercepts, -1, 0, and 2, as we were looking for. So without knowing anything else about the graph besides its intercepts, we know it has to be the right answer. Okay, on to our last example for this video, where we will again see how intercepts come in handy. This problem here asks us to do the opposite of what we did last time. Now we are given a graph, and we are asked to match it to its function. Last time we used x-intercepts to do this, but looking at our answer choices, it's going to be very hard to find the x-intercepts of these nasty unfactored polynomials. Instead, let's try using y-intercepts. It's easy to identify the y-intercept on the graph. We just look at f of 0 and it's equal to 1. Now we can try to compare that with the y-intercepts of the functions. Now we can compare the y-intercept of positive 1 we just found with the functions for each answer choices as we see here. Now to find the y-intercepts of these functions, again, we want to plug in x equals 0. So substituting x equals 0 in all of these nasty, complicated polynomial functions, we see very nicely almost all of it goes away. And we're just left with very simply 0, positive 1, negative 1, and 0. Just those terms without x's. Comparing that with our graph again, which had a y-intercept of positive 1, we see only b has the correct y-intercept. So without knowing anything else about these really complicated polynomial functions in our answer choices, we know that b is the right answer just by matching its y-intercepts. That's it for this week. Make sure you get practice identifying these key features of functions for problems like the last two we just solved. X and y-intercepts are always going to be very useful for these problems. And if you have a quadratic, you can try to use Vertex form to get some more information as well. Next week, we will cover the same ideas, same problem types, but applying instead to exponential and rational functions.
Hope you liked the video. If you want to hear more and see what else we're up to, hit like and subscribe, and see a new video coming out from Point Avenue every week. If you want to talk to us, hear more about what we're doing, or have any questions, email us at contact@pointavenue.com. Bye!